Okay, this session is being recorded and will be posted later today to the recorded presentations page on this classroom page at my TCC Blackboard. On the schedule for today, we're going to cover chapters 11 and 12, modules 11 and 12 on design, network design, and troubleshooting. We were not able to meet last Thursday for the real live in-person lab because of a district-wide faculty meeting. So the 10.8.2 lab that I would have gone over last Thursday, I'll go over this Thursday instead, day after tomorrow Thursday, for the live lab session, which will be recorded as well. And the TFTP password recovery lab demo part, which is not a required lab, but something I just do to show you something that's going on, I'll do that, and I will record and post that on or before May the 6th, which is our scheduled lab work day. So next week we'll cover chapters 13 through 14, modules 13 through 14, the last two modules on virtualization and automation. Those are going to be presented as a form of about, there's a few over a dozen recorded presentations that are on the Cisco Academy page for this class, and I'll show you, I'll make a little presentation to show you how to click and find those easily and view those. Our final exam in the last week of class is coming up starting on May the 5th. The final exam will be turned on at 9 a.m. on May the 5th, and it will run for one entire week till May the 12th, Wednesday at 9 a.m. in the morning will be that 1 week final exam period. And that's the next Wednesday, that Wednesday on May the 12th, not next Wednesday, but May the 12th, Wednesday, is the final deadline for turning in all work. There is, I didn't write this down here, but there is a course feedback form. It's kind of a student satisfaction survey that I'm going to enable on the Network and Academy site. And Cisco has a business rule that you must take that course feedback form before you can take the final exam. So don't worry if you forget about it and you try to take the final, it'll pop up a link and you can take that. Okay, I'm going to go ahead and start going into the, let me stop sharing this. And I should be able to start sharing the first PowerPoint presentation. And our first topic is access distribution and core layer functions. So Cisco has a design philosophy of, now if you're a large company, you would use this model, like Tarrant County College would use this model. If you're a smaller company, you just might use a clap score or a two-layer type model. But and I've got a much better graphic than this show us in the next one. I'm going to show you that, and then I'll show you my better graphic. The access layer switches are these are the most inexpensive switches, like our Cisco 2960 switches. They're only about $500 a piece for it's got 26 ports on it, and that's what we use to connect our devices that need connection to the network, like an employee desktop PC or a student desktop PC or a printer or a server or anything that needs a connection to the network. We're going to plug into one of these multi-port switches that are scattered all over our enterprise in various wiring closets, because we're stuck with this 328-foot distance over that Ethernet cable that goes out from that Ethernet switch to the end devices. So we tend to place these wiring closets in every floor of a building. If it's a huge building that's bigger than 300 feet across or 600 feet across, we might need more than one wiring closet. These access layer switches connect to our desktop PCs with twisted pair cable, copper cable, like category 5, category 6 cable. And then they connect to each other and to the upper layer switches with fiber optic cable, because fiber optic cables can carry much more traffic and they can go longer distances. So these access layer switches, the only type of security they're going to have is the MAC layer subsecurity, the data link layer subsecurity we looked at earlier. In other words, I could say the switch port that goes to the dean's office, I'm going to have him memorize the dean's proper MAC address of his actual PC. And if someone gets into the wiring closet and unplugs him and plugs in their device won't have the proper MAC address and they won't have any connectivity. It'll cut them off. Distribution layer switches are the up layer switches that access layer switches connect to. So distribution layer switches, these are where we're going to do things like maybe it's a layer 3 switch and we'll do some routing on it. Maybe we have a separate router. If we're doing any type of access control list stuff, filtering security, we can do this at the distribution layer. And these distribution layer switches will in turn connect to the core layer, which is the high-speed backbone of the network. The core layer, we don't have any access control lists on it because access control lists slow down devices. They have to get a look at each packet and decide whether it's to be permitted or to be denied. So the typical diagram that you see, well, I think that's a fairly lousy diagram here. Look at this three-tier network, pin. So we look at this three-tier thing here. This is kind of vague. What does this mean here? So I've got a better graphic here I'm going to show. Let me see if I can stop this and share this tab. This is from a Cisco seminar. This is a much better picture of core distribution access. So here we've got our core layer in the middle, and then that goes to lots of different distribution access switches for the various things in our company. Like we have one layer that goes to the internet. We have one connection that goes to our data center. Because data center switches are a different type of switch than you would use for employee switches. And have to be much more rugged and much more high speed. We might have a connection for our WAN connections, our wide area network connections to our other facilities, our other branch offices. And then the three at the top would represent the floors and buildings at this particular location, where we're going out to distribution layer switch on a floor, and then it goes to the various access level switches that are in the various wiring closets on that particular floor of that building. I think this is a better diagram. That's why I want to switch to it. Okay, so let me see. Stop sharing this. Come back to share files. I was here. Does you remember where I was at? Now, if it was a smaller company, we might only have like a two-tier. Lost my pencil. We might only have a two-tier network, where if it was a smaller company, they might not want to have, a big expensive $1 million router like a core router, and then a $50,000 distribution layer router, and then our little $500,000 access layer switches. And that's kind of like a collapsed core. You would see that in a smaller basis, smaller network. So here's another diagram of core distribution access, where we're more of a hierarchically based network. And if you notice that the connections between these switches at the access layer and the switches at the distribution layer, they sort of form a triangle. Each access layer switch should connect to two up layer switches. So in case fault tolerance, redundancy, and any one device fails, like if it's an interconnecting link between two of the switches, fiber optic cable, someone's working on the water lines and they dig up and they cut the fiber optic cable, well, each switch has still got a secondary connection to another way of connecting to its up layer switches. Okay, scalability means I can add to a network without having to throw the whole original chassis out and start all over again. So for example, many years ago, we had a telephone switch in our admin building, and we ran out of slots for line cards for additional telephone lines. The college grew in capacity and got more students and got more employees. And they had to simply take a forklift and take out that entire old chassis and put in a new chassis that had more slots for more line cards. That's not scalability. You got to throw the whole original thing away. Scalability means we can add more capacity to the system without having to throw everything out that's already existing. So as an example of that, when we built our new air conditioning building a couple years ago, we were able to simply run new fiber optic lines to that building and put switches in that building and add to our existing capability. We didn't have to completely throw out all the existing equipment that was on the rest of the campus. Redundancy is this idea that if we use this sort of triangle topology and connect every switch to a couple of other switches, then if there is a switch that fails, or a fiber optic link that fails, or a power that fails, we can have an alternate path for our people will still be able to do their job functions and do their productivity. And they won't stop just because of one link has failed. You A+ guys, when you took the A+, you talk about RAID drive arrays. So you could have a RAID 5 array of 5 hard drives. And any one of these drives can fail. Doesn't matter which one fails. Any one of them can fail. And you'll still have all your company data. You won't lose your precious, probably what's the one file you can't afford to lose under any circumstances? Your accounts receivables file, because you got to know how much money that your business partners and clients owe to you. Now, we already talked about redundant paths in Ethernet-based networks can form broadcast loops and other problems. So spanning tree protocol is used. And then we can also do link aggregation like Ether channel if we want to bond lines together and get more bandwidth. The failure domain is if one thing fails and the entire building or facility goes out, that's too large of a failure domain. We want to narrow things down so that if any one thing fails, it affects as few people as possible. Now, I ain't going to run 2 fiber optic cables between your student workstation and a couple switches back in the data center. That's impractical. So if your one Ethernet cable comes loose on the back of your PC, you're a single failure domain. You're the only workstation that's affected. If that switch that you're plugged into in the wiring closet fails, you and the other 23 people plugged into that switch don't have any connectivity anymore. But everybody else plugged into the other switches continues to have connectivity. So we want to try to design things in such a way, when possible, that the idea is any one single physical thing can fail and the fewest number of people are affected. So these switch blocks, these triangle shaped switch blocks where we run a triangle shaped connection between the access layer switch in the lab and 2 up layer switches, if any one device fails, the network shouldn't go down. Or if it does go down for some people, it will be for as few people as possible. Now, we had a topic before about Ether channel. Normally, if I run 2 wires between this access layer switch, here's an access layer switch down here, and I've got this sort of triangle connection between the 2 upper layer switches. And so if a cable gets cut to this switch, I'll have another backup connection to the other switch. If I want to run 2 pieces of fiber optic cable to the library where this switch is and to the ACB building where this is, well, why can't I just bond those channels together? An Ether channel, which is Cisco's trade term for link aggregation, means linking 2 wires together and aggregating the total bandwidth. So instead of getting 10 gig of bandwidth to the library, I can bond the 2 fiber optic channels together and get 20 gig of bandwidth. And we call those port channels, and they acted just like an Ether channel, and we could bring them up and down and make them trucking ports and things like this. Now let's expand the access layer. What we have done at the college is put in a very, we pretty much have wireless access from everywhere on any campus. So instead of running one of the switch ports on the switch 2 to all desktop PCs, we're going to take one of those ports and run it to a Cisco wireless access point. And then you can come in with your, your own devices, your tablets or telephones or laptops or whatever has Wi-Fi access, and you can connect to our network using this. We do provide this as a free service, and it doesn't have really, it's not encrypted, it's not WPA2, it's totally unencrypted, so just be aware that when you bring in your personally owned Wi-Fi attached device and you attach to our network, that we're not encrypting anything. If you can use a VPN if you want to yourself, and you can encrypt your data, but it's not encrypted. Someone could run Wireshark and see data that's on there. And since it's a publicly accessible network, we have to put some security restrictions on it where it's not wide open access, where somebody could bring in a virus-ridden Wi-Fi device and try to break into the web advisory server. Now, we talked before about the open shortest path first, which is the only routing protocol right now that we have as a CCNA objective. And in a large network, you would have an area 0, and then you would go to your branch offices, and there would be other areas. You have to have an area 0. So in the Tarrant County College network, the district headquarters is our area 0, and then our various networks they start. You don't have to go 1, 2, 3, 4, 5. You can go any order you want to. So every time anybody puts up an OSPF diagram, they think they're great comedians, and they've always got to say, "Oh, area 51." This is our flying saucer research network. So it's not a true OSPF diagram unless you put in that little joke. And the idea behind dividing our network into areas is any instability in one area of the network won't affect other networks. Now let's look at some switch hardware. Cisco has a line of switches, and you can get them in 12 ports, 24 ports, 48 ports at various speeds. The 2960 switches we use in the standardized Cisco labs have 24 fast Ethernet ports, which will go fast Ethernet or standard Ethernet speed. And they have 2 gigabit Ethernet ports that can go gig, fast Ethernet, or regular slow 10 megabit Ethernet speed. And they also have a little transceiver plug in them. You can plug in a fiber optic transceiver, and you can use fiber optic connection to upload, to go to an uplink instead of using slower twisted pair cable. And Cisco manufactures different switches that have different features you may want. Our switches in the lab don't have power over Ethernet. The switches in the wiring closet that plug in our student machines in the lab, they have to have power over Ethernet because they have to support the power over Ethernet Cisco IP telephone sets we have on our campus and our Wi-Fi access points. That way we don't have to have an electrician come in and run a separate dedicated circuit for us to plug in a wall wart power supply transformer in to make them work. Cisco has bought Meraki, and they make a more of a small business level type of switches. They don't have the GUI. They don't have the Cisco COI. They have a management GUI, kind of similar to when you go into your home router and you set it up. You don't have a CLI. You have a GUI that's used to set it up, and that's a set of a low cost. Now at the bottom of the picture, we've got the very expensive switches that can have thousands of connections in them, and we can use them to aggregate a connection in the multi-story office building, a bunch of users. We can use them in our data center to connect all our network attached storage attached network, rack mount servers, and connect them together at very high speed. And these are switches that typically can run up to $1 million. If you're a service provider, you would need to connect all your different clients, your internet service clients that are buying access for you to use your high-speed connection to the internet. So these can be very large, expensive switches too. Now, switch form factors talk about what kind of space they take up. Here's fixed configuration switches. So here's some switches that are kind of similar to the 24-port switches we have in the lab. They're fixed configuration in that we're stuck with whatever came with them when they were manufactured. They don't have any option slots. You can't plug anything extra into them. And these can be stackable or non-stackable. Now, our switches in our lab are not stackable. The stackable switches have a special plug on the back that you can sort of daisy chain, like up to 9 switches together, and make them sort of a low-cost chassis switch. So these switches tend to be the most inexpensive switches, these fixed configuration switches. You're stuck with whatever, you buy whatever switch with the capabilities you need, and you can't add on to it. Now, if I buy a 24-port switch and then I've got 30 new employees, I can buy a couple more 24-port switches and just add those to the other switches in my wiring closet. Chassis switches are the type of switches that have line card slots in them, and you can plug in, the big models can hold a couple dozen slots, and you can plug in a fiber optic connection slot with 12 fiber optic connections, and you can plug in an Ethernet card slot that's got 48 Ethernet RJ45 category 6 connections on it. And we can upgrade our chassis in the field by just adding another card or replacing a slow card, an older card with a newer card. Now here's the back of a bunch, 1, 2, 3, 4, 5, 6, 7, 8. It looks like there's 8 switches there that are connected. There's some special plugs. These look, from the front, they look like our switches we have in the lab. They're 24 or 48 port switches, 1 rack mount space. But on the back, we can sort of connect your ring between them with these stack cables. And the switches appear as one virtual switch. I can have one IP address and telnet to that one IP address and get access to those whole banks of 8 or 9 switches as if it was a chassis device with 8 or 9 card slots in it. And he mentions a rack mount unit. A rack mount unit, or 1U, is 1 3/4 inches high. So when you buy a rack to mount stuff in, it'll be 44 rack spaces high or 66 rack spaces high. And you can know how many devices you'll be able to stack in that rack. Port density refers to, when we look at our switches that are present in the Cisco lab, they're 24 ports. Actually, they're 26. They're 24 regular ports and then 22 uplink, and 2 uplink ports that are higher speed. So the port density is, if you look at the switches, there is a blank real estate on the left-hand side of our switches in the lab where there would be room to put 24 more ports. Now, our switches are fixed. You're stuck with whatever you get with when you buy that particular switch model. You can buy a 48-port switch model instead of a 24-port switch model if you want to. So in our connections, switches that are in the wiring closet around the corner from the classroom, they use a bunch of 48-port devices because there's precious little space in that wiring closet. And they've got to plug all these hundreds of devices that are present in our business building together into those 48-port switches. And also those switches have power over Ethernet and high-speed fiber optic uplinks that would be appropriate in our core distribution access environment. So if I buy a big, expensive chassis-based switch, a modular switch, I can mix and matching, put as many fiber optic connections and as many fiber optic connections and twisted pair copper connections I want on there. So in this case, this Catalyst 9400 switch, we can have up to 384 switch ports in it. The electronic circuitry that's in the switch, the fabric, the switching fabric, the backbone of it, there's a thing called the forwarding rate. In other words, if I have a switch that's at a data center and it's connected to a bunch of 10 gig servers and rack mount virtual VMs, I have to have very, very high performance switch that will forward all those ports. Simultaneously, I want all 48 ports on that box to be able to go 10 gigabits up and down at the same time. Very fast forwarding rate, wire speed switching, very fast switching fabric. An entry-level switch wouldn't have the ability to do that. And switches that go to access layer devices like employee PCs, these employee PCs are not all simultaneously uploading and downloading at 10 gig every second. So you can have a lower performance, lower cost switch to handle them. If you try to use a lower performance switch in a data center or in a core distribution backbone setting, it's not going to be able to run at full speed, and your bandwidth is going to suffer. So what data rates can we have? Well, we've given up on 10 megabit standard Ethernet, so we're usually going to be at least fast Ethernet, gigabit Ethernet. Today at our school, everything is gigabit to the desktop. You can plug in any device up to a gigabit at your desktop, a TCC-owned device, our corporate estate. And the links between the backbone switches in the wiring closets to the rest tend to be 10 gigabit and 100 gigabit speeds because they're carrying aggregate data of, for example, in our business building, we've got a couple of hundred PCs, and they've all got to go into a couple of fiber optic cables going to the underground tunnel connection that connects them back to the rest of the college campus network. So access layer switches usually don't need to operate at full wire speed. They're limited by their uplinks to the distribution layer, and you're not going to have 200 people simultaneously doing running Windows Update and uploading, downloading service pack number 1 that's 10 gigabytes all at the same time. Power over Ethernet is a feature that allows that single twisted pair Ethernet cable with 8 wires in it that goes from the switch port to your desktop PC, and if it's running gigabit Ethernet, it's using all 8 wires at the same time. What if we could also run a little direct current power, DC power, for something like an IP telephone, or an access point, a Wi-Fi access point, or a surveillance camera, IP surveillance camera, over that existing network cable? These devices typically don't need a lot of power. It's about as much power as a Christmas tree light bulb. Just 5 or 10 watts, something like this. So it's fairly easy to simultaneously feed a little bit of electrical power through these 8 wires, and at the same time allow the full 1 gig or 10 gig of communication over those wires. This does add expense to the switch. It adds a few dollars per port for the extra transistors to provide the power over Ethernet power to each device. So our $500 Cisco switches that we use in the lab don't have this. If you bought a 24-port switch and had power over Ethernet on it, it would be more than $500 because it had that extra circuitry in it. Okay, I hate this term, multi-layer switches, layer 3 switches. What the heck is this? A switch, or we used to call them bridges, is a data link layer device. It's a layer 2 device. He makes his forwarding decision based upon the destination MAC address in that Ethernet frame. He looks in the MAC address table, it opens up a virtual circuit and makes the connection take place, or if it's a broadcast, he's compelled to flood that broadcast to all the other ports. But the electronics have gotten so good, these very little integrated circuits, we call them application-specific integrated circuits. These are custom chips. You can get a custom chip made to do any function you want, so long as you want at least 1,000 of them. You can get them done fairly inexpensively. And then you can put that custom chip in your box instead of having to use a bunch of separate legacy smaller chips and do all the wiring and hook them together. This lowers the cost of the device, and it increases the reliability of the device. So multi-layer switches, since they have these essentially application-specific integrated circuits, similar to circuits on a desktop PC motherboard, we can add some layer 3 functionality. Even on our cheap $500 Cisco 2960 switches we have in the lab, those switches can do a little layer 3 stuff. They can do static routing. They can't do OSPF. They can be a DHCP server. So it can take sort of a load on upstream router off that router's burden and move this down more to the switch level. But I don't like the term multi-layer switch. Darn it, a switch is a layer 2 device. A router is a layer 3 device. So if you're choosing a switch, what are some of the considerations? Well, of course, you have to worry about the cost. If you're working for one of those companies where you're the chief IT guy and you report to the chief financial officer, oh, I'm so sorry, that's bad. Chief financial officers are very smart about money, but unfortunately, they regard every single expense as something to be reduced. So when you say, oh, I need to buy a switch that's $1,000 more, they're going to say, well, why can't you do with the other one? I'm not going to approve this. Now, if you're fortunate enough to work at a company where the chief IT guy, the chief information officer, reports to the chief executive officer, he's a peer with the chief financial officer, and he therefore has a place at the table. He can talk about technology value I don't think it should be called the IT department. I think it should be called the Technology Value Center. We bring value to the enterprise by using some technology. Some of this technology is expensive, but in the long run, it's going to make us more money. Port density is, well, our switches are just 24 ports, and they have that blank sheet metal on the left side. You could get that exact same switch from Cisco with 48 ports instead of 24 ports on it, and it wouldn't take any more space. Now, we talked about power over Ethernet. Some chassis-based switches will have the ability to plug in extra power supplies. So if power supplies fail quite a bit, more often than the other component, because they're generating a lot of heat and taking the 277 commercial voltage and converting it to the voltages, DC voltages that the digital circuits need. So it's possible in some devices to have redundant power supplies. If the one power supply fails, another keeps running. Think of a RAID drive array. One drive fails, we keep running. The switch should provide continuous access to the network. It should be very reliable. And what port speeds do we need? The switches that we use in the Cisco lab are they're only fast Ethernet for the main 24 ports. The ports that we use in our switching in our wiring closet around the corner that goes to our real network, those are gigabit Ethernet. I would argue that you need gigabit Ethernet as a minimum speed in today's technology. We're doing so much bandwidth intensive stuff like streaming audio and video. The frame buffers, the memory chips that are present in the switch, there's a couple different ways we can do this. We can have dedicated memory chips for each individual port channel, or we can have shared port channel. And this is going to depend on whether, if you're using servers, something like that requires a lot of bandwidth, it makes more sense to have dedicated memory for those server ports. And then we mentioned the scalability. Switches that are just fixed configuration switches like our 2960s, what do you do if you need more ports? You buy another switch and you jumper them together. If it's a stackable switch, you just add another switch up to 9. Cisco allows up to 9 in the switch stack, and you jumper them together with those special umbilical stacking cables on the back of the switch. If you're using a chassis-based switch or a modular-based switch, you simply locate a free slot and plug a new card into it. Now let's look at router hardware. Switches make their porting decision based upon the destination MAC address, and they use the MAC address table and they memorize them. Routers look at the network prefix, just the network portion of the address, and then they look on their routing table. And if the router has knowledge about that destination network, he'll use the exit interface or the next hop IP address to go ahead and send that router to his chosen route one more hop to his destination. Routers can be configured to select an alternate path if a link goes down. So we can have like a high-speed link and a backup ISDN link or Metropolitan Ethernet link. And if one link goes down, he'll automatically use the other one. All hosts on the network specify the IP address of the local router interface as their default gateway. So if we're on the network, let's say we're on your home network, and the network prefix is probably 192.168.1. And your router is probably 192.168.1.1. Unless you're on the weird telephone company, yeah, the telephone company, they are 192.168.1.254. They use the last address instead of the first address. But all host machines on your home network have to be 192.168.1. something, and they all have to have the proper subnet mask of 255.255.255.0, and physically they all have to be plugged into your home router or Wi-Fi connected. So routers do other things. They don't broadcast. They don't forward broadcasts. Broadcasts are of local interest only, locally significant only. They're only ARP requests and ARP replies. They're only DHCP broadcasts. Routers connect geographically separated locations. Your home router has 4 Ethernet ports for your LAN at home, and it has that WAN port that connects to your cable modem. And we can group in a company, we can group the marketing department and the management department and the advertising department and the factory floor production department with different routing subnets and provide security or control traffic. So we have our branch offices. We have our Cisco 1941 routers. This is what we use in the lab. And the newer generation of Cisco routers they actually run in Linux. And they're the 4000 series. Our routers are ISR version 2, and these new routers, ISR 4000 series routers, they're about the same cost as what the routers. Our routers are about $1,000 a piece. A small branch office router is still about $1,000. So the newer routers, the Cisco 4000 routers, still have the same type of connections. They have a console port. They have a couple of Ethernet plugs. They have slots where you can add a serial port or add a 4-port LAN switch card and so forth. The more expensive routers that an internet service provider or a service provider might buy, or a really large company, look at these things. It's the size of a refrigerator. It's so big. And these are like $1 million routers. These are their 9000 series routers, their new series of routers. So service provider routers, and the one on the right, we've got the door open and you can see all the slots there. And we're getting a little bit of Cisco marketing fluff here with network convergence system. There is a line of ruggedized routers, industrial routers. If you're in a noisy, dirty, oily environment like on a factory floor, a regular old switch just might clog up with the lint and the oil droplets in the air. So these ruggedized routers are built to withstand these environments. Extreme variations of temperature, extreme variations in dirty air, and things of that nature. And so they're the same exact function as a standard 2960 switch. They're just ruggedized to where maybe they can run off factory floor 24-volt DC, and they're not going to clog up if it's next to a machine that's a lathe that's cutting stuff and oil droplets in the air. It won't cause the device to fail. So they are higher cost because of these extra ruggedized features, but you might need them on a factory floor. So here is a switch to connect to small and medium-sized businesses where we have a few switch ports. It's fanless. Have you noticed our switches in the lab have a fan and they're kind of noisy? You normally want to put those in a wiring closet. Well, what if you have a small branch office with just 4 or 5 salesmen in it? And there's going to be no servers there. They just want a switch to connect back to the home office. And they don't want that switch to make any noise. It might not be able to go in a wiring closet. It might just sit on a desk somewhere. The Cisco 9000 and 1000 series are there. This looks like the same photos before. Very high capability, $1 million scale routers that a big company would use or a service provider would use. And more in Cisco marketing stuff with their 5500. The system looks like it's got quite a few slots in it. And you could use this, for example, in a data center. TCC has a big data center downtown at our Trinity River campus, where the trend these days is to remove all the work group servers from the individual departments and put them all in one location where they can be controlled more easily and have high speed and more easily backed up. Now here's a rugged version. It has a connection for 32 volts DC. We can get factory floor wiring, or we can use a wall wart transformer to do this. And it's designed for harsh environments. Okay, hang loose a second. Let me stop this. And we go to the next one, which is troubleshooting. And let's look at topology diagrams. We have a logical topology, pencil on, pencil on. So there's our logical topology. It's kind of similar to what we see on the front page of a lab. It shows us the logical connection between them, but it doesn't really show like the room number or a blueprint type thing. And the physical topologies look more, this physical topology on the left, that's a very good physical topology. It would look more like when we use the physical mode of packet tracer and we drag and drop a router and a switch into a rack, and you can see the routers on the top and the switches below it. That's more of a physical topology diagram. To document our network devices, we would document such things as what is the router model number? What interfaces does it has and where are they connecting to? If it's a switch, we would document, well, it says 2960 switch. Port 1 and port 2 are trunking to the next switch. Our end systems, like servers and PC workstations, we can document those. You know, what's their MAC address? What's their IP address? What's the DNS server address? Many companies tend to overlook the value of proper documentation, and the problem arises when something goes wrong. If you don't have it documented and you know what it should be when things were working okay, then it's much harder to figure out what went wrong. Whereas when you have all the documentation about it, you can check and make sure that it matches the levels in here, that all the things you've recorded about its configuration and the documentation, you can check for misdocumentation, try to figure out what went wrong. So there's something called a network baseline. Let's take a baseline of the network at certain times and do it on Monday morning when everyone's starting to log in. A little bit of surge of traffic there. Do it at 4:30 Friday afternoon when everyone's decided, I better get something done for this week because I look good, and then log off. Do it on the last business day of the month or the first business day of the month where everyone's running their end-of-month reports. And we want to get an idea here of what kind of traffic are we normally having on slow days and fast days and busy days, so that when something goes wrong, I can look at my baseline measurement and look for something that looks odd. It doesn't fit that. And maybe is it a network problem? People always blame the network. Oh, it's the networking, it's not working. Well, it's usually not the network. It's usually a problem with some new guy in the app dev department, application development department, wrote a program, he's blaming the network, and in reality, his code is bad. So you need to be able to, as you're a network guy, you need to be able to defend your network. You can pull up your simple network management protocol reports and show that, gosh, we're not having any problems with the network. It's full speed ahead here. Must be your bad code. Programmers don't like hearing that. So what type of data are we going to collect? Not too much stuff. Let's choose a few variables. If I collect too much data, it's going to be too much. So start out small, maybe fine tune along the way. How about interface utilization and CPU utilization on the routers and the switches? Yeah, I can show CPU processes on the router and see how busy it is and how busy it's been over the past 5 minutes. And that's something I can start to measure. Now, we don't want a router to be over, once it starts creeping over 50 or 60% utilization, it should probably be replaced with a more powerful router. We're getting too much traffic. Well, we can track this. Let's identify our devices and our ports of interest. So in this case, we're looking at the PC1, which is our administrative terminal. We're looking at 2 servers, server 1 and server 2. And we're looking at our ports on our switches and our router interfaces on our routers to see what we're going to be measuring. How long should we capture the data? Well, maybe 1 week. That'll capture the Monday morning rush, the Friday afternoon rush. Certainly no more than 6 weeks would be required. So as an example, as an average, maybe 2 to 4 week baseline, we'll measure that. Maybe be sure to capture end of month reconciliation report blitz of data. We can use the Cisco devices, show commands on the Cisco devices to capture some data. Like show version will tell us how long the device has been running before it had an error and had to crash. We can show our IP interfaces and look at things like how many collisions, how many errors have we had on the physical interface ports. A lot of things we can measure, which is plain show commands. This one is the granddaddy. If you have a support contract with Cisco and in an industrial environment and a commercial environment, you have to have maintenance with Cisco. So that way, if one of your devices fails, they're going to send you a new one by the next day morning, express delivery, and you'll be able to put that new switch or router in place and continue running because your network is crippled without that device. If you call Cisco's, they call it SmartNet, is their tech support department. They do all software and hardware support for Cisco devices. If you have a support contract with them and you call them, you're going to get a Cisco tech engineer. He's going to say, type the command show tech support and capture that as a text file and email it to me. And that's going to be a sort of a combination of all these commands you could run on the device. It's going to take it about 5 minutes for it to run. And you're going to capture that using Terraterm. Just capture that to a notepad file. You'll send it to the tech support engineer, and he'll look at that. Instead of having to ask you to type, show this and show that, he can look at that, and if he's a good tech support engineer, he'll be able to quickly look at that and maybe be able to determine right off the bat what your problem is. Let's look at this troubleshooting process. This is the 3-step troubleshooting process. So the stage 1 is we're going to, warning, this is the 3-step, there's a 7-step one coming up. This is the method that's been around for about 7 or 10 years now. They decided recently to go to a 7-step process and flesh it out a little bit. Stage 1, gather symptoms. You're going to look at the device. Maybe you ask the user what's going on. Then once you've gathered enough symptoms, you're going to go to stage 2. And I think I have a theory, I have a hypothesis that this is the problem. And then I'm going to go to stage 3 and I'm going to attempt to correct that problem. If it fixes the problem, I'm going to add that to my problem solution database and close the call. If it doesn't fix the problem, well, I made an incorrect hypothesis. I'm going to go back to stage 1 again, maybe gather some more information and come up with a second hypothesis or theory as to what the problem might be, and then see if that fixes it. And you complete this until you actually correct the problem and you can close your incident. So this has recently been fleshed out to a 7-step process. We're still going to define the problem and gather information and analyze information and eliminate possible causes. That was the first step of our other one. Then we're going to propose a hypothesis, see what we think it must be. Then we'll test it. We'll implement the solution, see if it fixes it. Now notice this, create a rollback plan. Anytime you're in a troubleshooting process and you try something to fix the problem, it doesn't fix it. What should you do next? You should immediately roll back your thing that you did, your configuration change to what it was beforehand. It didn't fix the problem. As a matter of fact, you might have created new problems by changing the configuration. So you should always roll back to the original state it was and try another solution that might work. Once we get it to work properly, we're going to verify that it did fix the problem. We can go to the step that we solved the problem, tell the users their problem is fixed, and we'll document it in our company database. It's called a problem solution database that we use in our company to keep track of people that call the help desk and say, I can't do this, or smoke's coming out of the printer, whatever the problem is. Now, when we question our users, we don't want to try to overwhelm them with technical jargon. They're probably not that technically savvy, but we want to ask them, in plain English, questions about what's working here, what's not working. What's the scope of the problem? When I did troubleshooting with customers in the 90s, when I had a very large psychological database product that we sold to our customers, we would ask questions like, they'd call and say, well, the product doesn't work. And I would say, well, did you recently install or change any other software on your machine that might have messed up our machine? Because sometimes some software products installers will collaborate with other existing programs that were perfectly working before he tried to install this other program, this troublesome program. Is it a problem that's constant or is it intermittent? So constant problems are easy to fix because they're there and they're broken and stay broken. An intermittent problem is like, well, your car squeaks, you take it to the mechanic, and as soon as it gets to the shop, it doesn't squeak anymore. So the mechanic can't figure out what's wrong. That's an intermittent problem. Here are some Cisco iOS commands. We can check network connectivity with ping. If ping proves end-to-end network connectivity between 2 arbitrary host machines that you're pinging back and forth from. If ping fails, well, gosh, I don't have complete connectivity here. I wonder where the problem is. Let's step to traceroute. And traceroute, which I call ping on steroids, will show me step by step as the packet progresses to the network. And if it fails between router 5 and router 6 of a 10 router path, now I know exactly where the problem is between router 5 and router 6, instead of where could it be along these 10 routers. Telnet is a utility that we can connect to a device. If we've done that line BTY04 password Cisco login lines, we can telnet to it. Within our internal network, telnet's probably safe. In the Cisco lab, it's just a sandbox lab. That's totally safe. But in a network where we're worried about other people seeing our traffic, we can use secure shell because that encrypts all the data. Certainly, if I was going to connect to my $7 a month internet web server that I use for storing my family photos or whatever, I would want to use some type of encryption attached to that. Secure shell to get to a command prompt or HTTPS. Show interfaces, show IP interface brief. Quick explanation of which interfaces are up and up and what their IPv6 addresses are. Look in the routing table with a show IP route. In my experience with teaching this CCNA objectives for over 20 years now, I can usually, when students make a mistake in the lab, I can usually find the problem pretty quickly by using show IP interface brief and show IP route. That'll usually tell me what the problem is. Now here we have our dreaded, feared, and hated 7-layer reference OSI reference model. And we can see that the physical layer, well, a device that corresponds to the physical layer is like a hub. A hub is like a dumb device. Don't be a member of the hub club. Hubs are dumb. And we have smart switches. Oh yeah, they understand Ethernet frames. They have MAC address tables. They're data link layer devices. Remember when I complained about layer 3 switches? No, switches are data link layers. So here's our multi-layer switch up here. It's a switch that also has essentially a router on a circuit board in it. So at the network and transport layer, the router is going to forward data using the network address destination information. And if he's running access control lists, maybe he'll also go up to the transport layer. Maybe we want to permit port 80 incoming web traffic, but deny port 23 incoming telnet traffic. We can do that with access control lists for security and filtering traffic. And then the top 3 layers, the session, presentation, application layer, the 7-layer OSI reference model, are roughly equivalent to just what we call the application layer of the TCP/IP model. So in systems run all 7 layers. They run application programs that need access to the network, and eventually the end system is going to encapsulate that data into an Ethernet frame, and the Ethernet frame will go out to the physical layer in the form of electrical bits representing 1s and 0s. So some troubleshooting methods are, quite a few problems are physical layer problems. If I start at the physical layer and go up, bottom up, check for corroded cables, replace the wire, see if that fixes it, that can fix many problems. If you think the problem is a software problem or a configuration problem, you can use the top-down method. Go from the application layer on down until you run into the problem. Once you gain a lot of experience in this field, you can use something called divide and conquer. For example, you might have been working enough to where you see a problem and you say, I remembered that type of problem before, and the problem was the subnet mask was incorrect. So you jump right to the network control panel and check the subnet mask, and if it's incorrect, you try to fix it to solve the problem. Substitution problem, the first hot shot field engineer guys, if they have a problem, they start replacing circuit boards so it starts working again. Then it starts working. Or it could be he has an educated guess. I call this a WAG or a wild ass guess. We're going to just guess on it and see if it fixes it. As you get more experience, your guesses get better. So if it's a software problem, maybe I'll go top down. If it's a hardware problem, I maybe go bottom up. If I've had experience with it before, maybe I'll use divide and conquer and sort of zoom into the layer that I think it is. So some tools that we can use for troubleshooting. We can use network management system tools. We can monitor devices. We can look at their configuration. We can use ping and trace route and try to see what kind of network problems we're having. Knowledge bases are put out by the vendors of the products. Probably the most famous one is the Microsoft's TechNet, which they used to charge you to get, but now it's totally free online from Microsoft. You get access to the same exact technical database as if you paid. It's over $300 now for the tech support center. Product support services in Irving. If you call with a problem with Microsoft, they'll attempt to solve your problem for a fixed fee. And they have the knowledge base that they use. You have access to that for free if you want to try to figure it out yourself. Baselining tools. We talked about baselining the network. We're going to use things like Wireshark and the tools in Windows that allow you to look at the system monitor and see what's going on and get an idea of, how busy is the disk drive and the CPU on the server. How busy are these network devices, these routers and switches? So here's a screenshot of the Wireshark program. Wireshark is very good because it can go down and capture an encapsulated chunk of data, and it shows you the physical layer, the data link layer, the network layer, the transport layer, the application layer. It shows you all those things, and you can zoom in and look at problems. It's so powerful that if you're using an unencrypted protocol like FTP or Telnet, you can see their passwords. That's one of the reasons why Telnet is not very secure in an environment where other people can easily run a Wireshark and see passwords. So we can use those to troubleshoot network performance problems. Now let's look at some hardware troubleshooting tools. Digital multimeters, which you can, let's see, let's go to, what's the Chinese tool store place called? Harbor Freight. Okay, you can get a coupon and get a multimeter for $2 or free. And you can use that to measure a wire. Is the wire good from one end to the other? I can measure the resistance of the cable. I can check for proper voltages. The next step up are cable testers that I can plug a Ethernet cable into, and the cable tester will make sure pin 1 goes to pin 1 on both ends, etc. If there's any shorts in the cable, it'll tell me where the shorts are. These testers are typically in the $100 range. Cable analyzers, when you have a contractor come in and do the wiring at your facility, you're going to ask that the cable be certified. Like, for example, if you're paying for Category 6 structured wiring system with a 20-year guarantee, you're going to want to test and make sure all those cables and connectors were installed properly. These are $3,000 range devices. These have the time domain reflectometers in them. If there's a fault, they can tell you how many feet away the problem is. And they can certify copper and fiber wiring installations. Network analyzers we're getting up into $10,000 and $12,000 range now. These are devices, Fluke makes one that you can go to an office and plug right into the RJ45 Ethernet connector, and it'll attempt to do a DHCP connection back to the server and check the network connection and give you a lot of useful information on a small handheld device very quickly. And Cisco prime name is Cisco Marketing Fluff. Now, we talked about Syslog as a means of, if you're on the router or switch and you're consoled in, you see all these messages appear on the screen and they scroll up and they're lost forever. But you can also send them to a Syslog server. Now, I'm using the word server. It sounds like an expensive box. You can use any cast-aside user workstation and just put a large hard drive in it. Large hard drives are very cheap. Hang it on the network and configure your Cisco routers and switches to all send everything that appears on the screen to the Syslog server. And then you can go back and make sure your clocks are synced with network time protocol. And then you can go to these Syslog server and look at all the log files and line them up with each other and try to track an intruder going through your system or try to track a network issue, traffic issue problem. And you can determine how verbose, how much detailed information do I want to send to the Syslog servers. You can go from a level 0 where there's almost nothing except I had to crash, all the way up to level 7, which is warts and all. You get to see everything that appears on the screen. At the physical layer, what are some of the problems and symptoms that can occur? We might get poor performance. We might have complete loss of connectivity. Well, our ping test doesn't work anymore. We can check with this. We might have bottlenecks or congestion. Oh, the routing protocols seem to be redirecting traffic to a slower route for some reason. High CPU utilization rates on a router or a switch or a server indicate that that device is starting to be becoming overloaded. We need to shift some of the load to another device or replace this device with a more capable device that has a more powerful CPU and RAM memory in it. Otherwise, we could have network performance problems. And then for our console error messages, well, we can see them if we're in the screen, but if a problem occurs, we're not logged in right now, we won't see it. And it's been lost off the top of the screen. So Syslog is useful that we can go back and see the log files of what happened earlier when we weren't yet not console in. So let's check for power-related problems. Are the fans running? Is there no gunk that would, cause the circuit to overheat? Are driver files, network interface card driver files bad? I won't call that hardware, I call that software. Bad cabling or grounding problems can cause problems with our packets and our frames. Let's look for damaged cables, the wrong type of cable, poorly crimped connectors because someone decided they would make their own cable instead of using a professional installer. Well, if you suspect a cable is poor, exchange it with a known good cable and see if that fixes the problem. Gosh, they're 47 cents each from Monoprice. Just carry a bunch of spares. Attenuation is the voltage on the wire that represents the ones and zeros. It sort of peters out, as we say in East Texas, and we need to gussy it up and put a repeater in there, or use a shorter wire or a heavier gauge wire so that we won't lose the electrical wiring that represents the ones and the zeros. Now, there's a lot of sources of noise in the outside environment. 277 volt lighting fixtures. Radio stations, like across from the campus, we got this giant transmission tower for the county public services, emergency services. I used to have a Novell network data center, and on the other side of the wall from the data center was the elevator motors for the entire building. So it was a lot of electrical noise. If we configure our interface improperly, wrong clock rate on the old serial ports, how about a half duplex, full duplex mismatch between two switches? We can have a bunch of Ethernet collisions we don't need to have if they were matching each other. What if I tried to take a $500 box and try to have it provide the performance of a $10,000 device? It's going to drop packets. It's going to drop frames. We need to, if we need that performance, we need to put in a device that can handle the performance. So if we're exceeding the design limits of a $1,000 branch office router, the CPU is going to be constantly overloaded. He's going to time out, and we're going to have all sorts of problems. At the data link layer, if we have no connectivity at the network layer or above, all the link lights are on, we don't have any physical layer problems. We have some type of network layer problem. There's a mismatch between frame types. There's too many broadcasts. The network isn't operating up to the baseline performance levels that we measured earlier. So this could be a cause of encapsulation errors. We used to see these on serial ports, like Cisco had the default encapsulation type for their serial ports was HDLC, but it only worked with other Cisco devices. We try to connect another vendor, Lucent or Nortel or Ascend or some other brand of router to the serial port, and they can't communicate. We need to switch to a different encapsulation type that everybody supports, like point-to-point protocol. We can have an address mapping error. We've got this ARP function that's supposed to line up our layer 2 MAC address with a layer 3 IP address. If that stops working, we're going to get mapping errors and we won't be able to communicate properly. Framing errors can be caused by noise on the wire, a bad cable, a faulty network interface device. How about duplex mismatches? And with the old serial ports, we had to make sure our clock rates were proper, because in the lab we were simulating the clock rates we would get from an ISP. Do not turn off STP. Just because you think you don't need it, you don't understand it if you're turning it off. We need to have STP on. If STP has a problem, it's usually we're trying to change our network too much, or failure is causing a link to go up and down. It's causing a lot of STP traffic as it reconfigures or reconverges the network. At the network layer, layer 3, the users are going to be fairly non-functional because they're not going to be able to ping. Ping uses ICMP, layer 3 protocol, to send echo requests and echo replies. And this will be noticed very quickly by the users. Your phone will start ringing at the help desk very fast. Or you may have a suboptimal performance. So this can be kind of difficult to troubleshoot. Could be general and network issues. Someone's changed something, something's come unplugged, somebody didn't notice it. Connectivity issues, ISP problems. Let's look at our routing tables. If the router doesn't have a consistent, proper entries in his routing table, if it's not in the routing table, he can't forward it. So make sure your routing table is proper, make sure your OSPF is set up properly, make sure your default routes are okay. Look up neighborhood adjacencies. With Cisco routers, you can type show IP OSPF neighbors or show OSPF neighbors, and you can see your neighboring devices, kind of like Cisco Discovery Protocol for OSPF. I can see my directly connected neighbors. And you can also show IP OSPF topology and see the topological database that he's picked the one fastest one. OSPF picks the best entry, and he keeps the others in the background. Now, if you're using access control lists and you're doing things like filtering at the transport layer, maybe allowing port 80 web traffic, but disallowing port 23 telnet traffic, access control lists have to be key. If it's a standard access control list, it's supposed to go close to the destination. If it's extended, it's supposed to be close to the source. Make sure it's in the right, correct interface in the correct direction. Make sure the order of the entries are proper. Don't forget about the implicit deny any at the end of an IP version 4 access control list. And we don't have to worry about IP version 6 access control lists anymore. That's been taken out of CCNA. But we still have to worry about the wildcard masks, the reverse mirror image of 255.255.255.0 reverses to 0.0.0.255. Now, if you're going to do crazy things like allow even addresses and disallow odd addresses, you can do that with wildcard masks. But you might be, if you're trying to do something weird instead of a whole subnet mask, you might see some errors there. It didn't do what you intended it to do. Make sure the correct source and destination ports are set. The established keyword is typically used where the TCP three-way connection has been made, sync-ACK, to check for when traffic comes back to the office or back to your home. Does that reply match my request? The established keyword will make sure the port numbers match, and he won't let the traffic back in unless that takes place. BootP and DHCP require source IP address of quad 0. Network address translation requires a valid address. So DHCP might not run properly over NAT. Now you might be able to configure the IPv4 helper feature, which will turn that broadcast into a unicast where you specify the actual destination address of the DHCP server, and then it'll be turned into, instead of a broadcast, now it's a standard IP unidirectional packet, and it'll survive the trip to the DHCP server. Similar issues with DNS and Simple Network Management Protocol. Here are some application layer protocols. We've seen most of these before. Secure Shell and Telnet. We're going to establish a connection to a router without having to physically be added. Hypertext Transfer Protocol for web stuff. File Transfer Protocol for downloading files. This is an unencrypted, completely unencrypted, including names and passwords, so watch out for this. Anybody can Wireshark snoop it. TFTP is what we typically use with network devices to load and save the configuration and the operating system file. If you're a cable modem customer and you pay and get a newer, faster bandwidth, they will send a TFTP file to your cable modem and change its configuration file, and you'll get the higher speed. Or if your TFTP modem manufacturer issues an operating system upgrade, they will use TFTP to update it for you. Simple Mail Transfer Protocol, not to be confused with its exact neighbor, Simple Network Management Protocol. Mail is for transmitting, sending email. POP is for receiving email. Simple Network Management Protocols we use with a network management workstation. DNS, which I call the Directory Information Operator of the Internet, maps an IP address to, we cannot expect, it is illogical, it is irrational to expect our users to type in 32-bit or 128-bit binary IP addresses to go to Facebook. They type facebook.com. Network file system is a Unix, Linux type thing similar to Microsoft's server message block that allows users to attach to a server and see shared files and see shared printers and things of that nature. Let's troubleshoot some IP connectivity. If we're using the bottom up, we're going to check our physical connectivity at the point where network communication stops. So let's say I run a trace route and it stopped between router 5 and router 6. I'm going to trot down to where router 5 is located with and check the physical connectivity between router 5 and router 6. Check for duplex mismatches. Make sure the data link and network layer addressing on that link between router 5 and 6 are proper. Make sure the default gateway is correct. Make sure the devices are finding the correct path. Transport layer functioning properly. Is there no ACL? Badly configured ACL is blocking traffic. And DNS, Oh, then on Reddit they say DNS, it's always DNS. Because DNS is the one function that changes host names into valid IP addresses. So here we have an end-to-end connectivity problem, and he's using this to do troubleshooting. He's using ping and traceroute to determine where the problem is. So if there's a problem with end-to-end connectivity, total end-to-end connectivity, ping will fail. Traceroute will tell us exactly where the problem is occurring, between which routers. Let's look at the physical layer and type show interfaces. Well, this is good. We have no errors, no input and output errors. We don't have any broadcast drones. We don't have any collisions, anything of that problem. We're looking for things like drops, input errors, output errors, which is probably going to be a corroded wire or corrosion on the wire or improper wire type or something of that nature. Let's check for duplex mismatches. I do show interface on this router and it's full duplex. I do show interface on this neighbor and it's half duplex. Oh dear. Full duplex machines think they can send and receive at the same time simultaneously all day long. Half duplex switches think they can only send when no one else is sending. So the half duplex router is going to freak out because the full duplex router is transmitting to him even when he's trying to, he says, I'm transmitting to you, you should not talk, says S2. S1 says, well, I'm full duplex, I can send whenever I want to. So we get lots of errors. We have to change both these switches to either both be half duplex or both be full duplex. In the defense of the hardware manufacturers, they've gotten pretty good in the past 10 or 15 years with making this negotiation between the two Ethernet ports to work pretty well. They'll both fairly reliably these days both choose full duplex or half duplex, whatever capabilities they have in common, the highest capabilities they have in common with each other. We can type the ARP command at a Windows prompt, ARP-A, and see the mapping between the layer 2 physical address, MAC address, Brennan address, Ethernet address of our workstations that we're communicating with, and their IP addresses. If it's missing from this table, they won't be able to, maybe there's some problem with ARP. Maybe they're in different VLANs and you didn't configure it properly. Okay, VLAN assignment. If I've configured two devices to be in the same network, but they're on different VLANs, oh, well, here's a problem here. That MAC address on F1 should be on the 10 VLAN, not the 1 VLAN. He needs to go back and replace that, fix that problem, go back and assign port 1 to be in VLAN 10. Let's make sure our default gateways are proper. Every individual subnet, which is a bunch of devices that are plugged into a single switch or a single VLAN on a switch, and there's a router with a default gateway pointing toward them, they all should have that same network prefix. They all should have that same network subnet mask, and they should all agree what is typically the .1 address, what is the default gateway that gives me my connectivity to all the rest of the other devices in my company network. So I can type show IP route to make sure the default gateway is proper. On the PC, I can type route print, and that will tell me what he thinks his default gateway is, and we can go and type ipconfig on the device if it's a Windows device to make sure the settings are proper. Now, IP version 6 default gateways can be configured manually, statically, or using some combination of Slack, English, I'm just updating attendance. Oh dear. He timed out on me. Hang list, I gotta relog into my TCC Blackboard. I mean, Web Advisor. Okay, spring semester 4. Attendance checking. Last. Okay. So in IP version 6, we have 3 different ways the workstation can get his address. He can either, well, 4 ways really. He can statically configure it, but if it's not static and then you click the box that says obtain the IP address automatically, which is normal, who wants to statically configure hundreds of PCs, then he can either get it from his default gateway, his friendly neighborhood router, using Slack. He'll get the network prefix from the router. He'll just make up his own interface ID. You can use a combination of Slack and DHCP version 6, or you can use totally DHCP version 6, where the DHCP version 6 router gives him his individual address, his slash number, it's going to be /64, his default gateway, his DNS, all this other stuff. Let's make sure that we have the correct path. We want to verify the path. So if a packet comes into a router. He's going to look in the routing table and see if there is an matching entry in the routing table. If so, he will send it to the best match that's in it. If there's more than one that match, he'll send it to one that's the best match. If they're both are equal, he'll round robin load balance. If there's no entry in the routing table, if a default route has been established, he will use it. If no default route has been established, the packet is discarded. So we want to use the longest match rule. If a routing table has ambiguous entries, we'll choose the one that has the most bits that match. At the transport layer, this administrator is attempting to tell net to R2 using port number 80. He's just attempting to see if the web server software is responding on port 80. Port 80 is all web servers listen at port 80 for incoming requests for their home page. We can check for access control lists. We can show access listings, make sure they're proper. Well, in this case, he put it in the outbound direction, in that direction instead on one port instead of another port. He moves it over and that fixes the problem. So the placement of access control lists is very important. Last step, verify DNS. Make sure DNS is working. What's our DNS troubleshooting tool? Is NS lookup. We can type NS lookup and then we can sort of peek into our DNS server that's if you're home, it's provided by your internet service provider. If you're a large corporation like TCC, we have our own dedicated DNS servers, and then we can see if there's a problem with that. If you don't, here's a common problem with cable modem customers. The DNS servers in cable companies are notorious for, if you mistype it, Microsoft.com, if you mistype it, you get targeted advertising. So you do not have to use your cable modem's DNS server that it gives you through the DHCP process. You can click the box on the DHCP portion of the network control panel and specify your own DNS server. Well, how about the Quad 9 project, which won't let malware come on your computer? 9.9.9.9, that's easy to remember. Google 8.8.8.8. Use one of those instead of your cable modem problem if you're getting a bunch of weird pages pop up whenever you mistype the name of a web server. I think that's it. Hang loose. I will stop the recording function.